I'm very happy to present our next speaker, Adina Williams, who's a colleague of mine at Meta. And when I asked her about the title for their presentation, she gave me two options, which I think speaks for the wide variety of things that they can tell us about generalization. So it was very difficult to choose between the two options because honestly, I wanted to hear them both. I think she's also presenting at the main conference with stuff maybe a bit more related to the option that I didn't pick in the end. So please, join me in welcoming Adina with her presentation, Evaluation After the LM Boom.
Thanks, Tuka. That was a super nice intro. I'm really excited to be here with you guys today. I love this community. I think it's doing really exciting work. And I'm also really happy to have followed Anna's talk because I think we have a bunch of synergies. And I feel like if I had written my talk after, I wouldn't have been able to fit them together as well. But it's like, yeah, you talk about things I don't talk about. And it's, yeah, very excited. Yeah, so I've been working on similar things to the generalization as a question for NLP for a while. And I think maybe I'm not alone in feeling a little bit of trepidation about the way things are currently going. So today I decided to, split up the talk into 3 bits. The first part will be like a little bit of history, very recent. A lot of you are probably there for a lot of this stuff. The second bit will be some about the present. So what is going on? Why am I frustrated? And what are the fallacies that people are committing in the evaluation space? And then the third will be a bit of future. So things that I've been working on that are trying to like move towards a solution to some of the problems that will be raised in the other parts. Cool. So let's start with a bit of recent history. You can think of part 1 too as referring to the GenBench of the GenBench, the Gen part, interest in generalization. So in the not so distant past, but maybe for some of you somewhat distant, like maybe 2015, 2017, somewhere around there, we used to kind of make models that would solve a single task. And we would do this with very simple data sets to train them, with train set here, test set here. When we started with our task, we would, fix something that we thought was interesting and relevant, something we wanted maybe to automate or something that was cognitively interesting. We would find and make a data set relevant to that particular task. And then we would split it into 2 parts. We would call one train and one test. And since they came from the same original chunk, we could say that they were IID, so independent and identically distributed, meaning that they came from basically the same distribution and that selecting one and putting it in one bin was independent from selecting all the others. We would also assume here that the test sets were held out. That means there's no overlap, whatever that relevant sense might be, we can come back to that, between the train and the test set. Presumably, or usually what the overlap would be no exact string match between those 2 sets. So note, at least that first bit, the IID assumption doesn't always hold. So there's many questions about this. Even if we take an original pile of data and split it into 2 parts, those 2 distributions still might not be the same. So let's say, do they count the same if they have the same set of bigrams with the same frequencies, or the same set of average sequence length, the same average token frequency? What is it that we count as being the same? This is something that the generalization community really cares about. Often you want to generalize to something specific, so to a different length or to a different token, like set of tokens or something else. But basically, this IID assumption has always been a bit squishy, but it's gotten squishier. Okay, so given those assumptions, what we would do next, you all probably familiar with this, is we would fit a model to data or train a model on data, the training set data, and we would say that it performed well if it got a good accuracy on the test set. Then we would say the model has learned. So from that good performance, we would also assume that the model has generalized from the train set to the test set, which were presumably the same distribution. Okay. So just to give a small example, this is a paper from my somewhat recent past when I first joined. This paper was written in 2017, which kind of the start of my history. And it came out slightly later, but it kind of straddled some of the changes in this history that I think are going to be important. So basically, multi-NLI, this data set, was made to benchmark sentence to vector models on NLU capabilities. So you're interested in, do these particular architectures, can they learn how to do natural language understanding? So it's kind of like a capability question. Now people just assume, oh yeah, the transformer can do everything. But back then it was like, is there an architecture that's better for natural language understanding in particular? So we crowdsourced this data set for natural language inference. You all are probably familiar with this task, but basically it's a task where you have two sentences, the premise and the hypothesis, and you ask what kind of the inferential relationship is between those two sentences. So if sentence one was, John saw a white cat, and sentence two was John saw a cat. Are they always true in the same situations? Is the second one false when the first one's true, or can we not tell? Basically, it should be an entailment, but as I'll probably know. So that was kind of the setting for this data set. The data set was also made for training models that were large at the time from scratch on this task specifically. So we had about 400,000 training examples, and then we had 10 development set examples and 10K tests. So we would train on a large pile, and we would test on a smaller pile. So note, I was kind of talking about generalization earlier. Whether the model is generalizing to the test set, you decide that there's kind of like an implicit argument in that idea of generalization. So what is the model generalizing to? To the IID test set, to something else. A lot of people leave that argument out these days and just say, oh, the model's generalizing. But like, if you don't know what it's generalizing to, it's kind of an incomplete statement. You can't really evaluate that claim. So it's good to, if you can, at least say somewhere in your paper, in your discussion, what the generalization axis, what you're generalizing to is supposed to be. This is also related to the GenBench taxonomy of assumed shifts, if you're familiar with that. Okay. So that was kind of the first classical NLP thing, which was just starting to phase out in 2017 when I joined this field. And what was phasing in at that time was the pre-trained fine-tune paradigm, which came about with like BERT, maybe you can trace back to Elmo or something else. But basically, this is kind of a new way of approaching the question of training a model for a task. We can think of this as the first turn of the screw. Hopefully that'll become clear later. So pre-train fine-tune, basically you would pre-train on a task that has lots of data and seems to be a good task for creating something like universal representations, often universal sentence representations. Around the beginning of 2017, NLI was argued to be one of these tasks. That's why people were interested in it in the first place. Well, I mean, besides nerds like me who just like logic or something, that's why the NLP people in general were interested in it. But now people are more interested in something like some version of LLM or some version of LM, so like mass language modeling or something else, or maybe down next sentence prediction, various different things that you could think of as like the universal pre-training task. And so once you've pre-trained a good model, you would then train again, which we then called fine-tuning, with trained test sets that had this held out and IID property on various downstream tasks. So you would say like pre-training, let's say a BERT model here, and then you would fine-tune on the MNLI train set and then test usually on the dev set, but you could also test on the test set as well. So in the sense, you're kind of increasing the amount of training and training on multiple tasks at the same time. In a sense, it's kind of like a synthesis between normal kind of specific task NLP and something like transfer learning. So you're fine-tuning to adapt. That's the terminology we used then. I think it's gone out of favor a bit, but fine-tuning to adapt your model to the distribution of the new task and the new task itself. So both of those things were kind of the goal of fine-tuning. So often pre-training and fine-tuning results, probably don't need to say this, but results in really good performance on many tasks, and it requires sometimes less annotation. But a lot of those training sets were already existing, so maybe that annotation point isn't so strong. So pre-training data is assumed to provide a good language prior, whatever that might be. And if the models perform well on downstream tasks, that's evidence in a sense supporting that the good language prior had been found, or at least that's kind of how the logic goes. I feel a bit squicky about it, but we'll see. Notes, of course, another aside, fine-tuning is still training. We call it something else, but it's still training. It's adding more data. The presumption is that if the fine-tuning data is much smaller than the pre-training data, then it won't change the model too much. It's just like a couple of little tweaks, but it's kind of hard to verify that. How many bits of information are we actually overwriting in fine-tuning? People have stopped asking those questions a bit. I would love for us to go back and ask those again. And also, of course, what counts as small training data has changed. So all of these things are a bit squishy and in flux. So again, back to our example, multi-NLI was sort of at the cusp of this change. It was created with a specific type of transfer in mind. It was domain transfer. So what was the text domain? So it tests whether the model can generalize what it has learned about NLI from, let's say, fiction to OUP press articles. So if it has learned something that's kind of abstract, something about the task of natural language inference, then it should be able to seamlessly switch over to this new domain, assuming that it learns a little bit about it, maybe from fine-tuning or something. So the large training sets and all these things really enabled a lot of early successes here on these things. So the question then with pre-training fine-tuning is the model generalizing to the downstream tasks? My answer would be absolutely. So even though the IID assumption is weaker, the test sets are still held out. So yes, it's something it hasn't seen before. There's no overlap. That's something like generalization. Of course, there are the caveats that the IID assumption is weakened, but also the data is larger and harder to investigate and characterize. This kind of echoes what Anna was saying. Please keep looking at the training data. It's super important. So yeah, with the emphasis on transfer generalization types, which came with this kind of pre-trained fine-tuning shift, test data is not IID to the trained data, just the fine-tuning part. So that was kind of all well and good. We'd kind of weakened our main two assumptions in two ways, but it's still, you know, the logic still kind of held. It still made sense to say we were generalizing to something held out. And that brings us up to the present day, which is yet another turn of the screw. So now what happens is someone, maybe somebody in this audience, but probably somebody somewhere far away, will pre-train a transformer-based model on some massive unlabeled data to do LM, which is, you know, an important task undergirding universal representations or language capability. Then those people will tune it in some way that probably isn't fully described. So maybe RLHF, maybe safety fine-tuning, maybe instruction fine-tuning, maybe just supervision. And they'll like do these tunings rapid fire, often kind of along the way of training without necessarily a plan, so I'm completely honest. And then they or we will test on many data sets. Often we'll recast something like multi-NLI to something that's more instruction fine-tuning friendly with like zero-shot, K-shot, maybe we should call it many-shot evaluation. So that's kind of the general thing we all operate under now. So with that change, where maybe there's no fine-tuning anymore before testing, there's been a bunch of change in evaluation. So training data is being way too large to investigate for test set leakage. So the held out assumption is really hard to maintain. Also, specific purpose test sets are saturating. So a model that's been pre-trained on a huge pile of data and tuned in various complicated ways might just do really well on all the test sets that we have, which means, and because of that, a lot of people are kind of enriching that fact a little bit more and saying, well, maybe we should assume instead that a model can do everything. So before we used to have the scientific kind of null hypothesis, which is the model can't do anything unless proven otherwise. Now people are leaning more towards the model can do everything unless proven otherwise. So this is a shift that kind of came about with this impressiveness of the new pre-training regime. There's also kind of this rise in open-ended prompt-based red teaming eval. This also came along with kind of the test sets saturating. So if there's no good test sets or they're hard to make, making a test set, let's say for multi-NLI or whatever, making that data set took a year, a little more than a year. If they saturate really quickly, then, you know, the evaluation people can't really catch up to the state of the art as well. And so then the state of the art people are just like, I got to test on something, let's try. Let's just red team eval, which makes some sense. But it's definitely a bit more kind of ad hoc and fluid. The emphasis that we had on transfer, say in the pre-training and fine-tuning stage, has now morphed into more of an emphasis on general purpose. So we want this kind of general purpose model that will do basically transfer to everything, right? So if it's transferring to everything, then it's not really transfer anymore. The idea of transfer has started to kind of fade from our view a little bit, and we've kind of gotten more excited about the idea of general purpose. Though, you know, it's not like really a stepwise change. It was kind of a gradual shift. I guess not that gradual, 2 or 3 years, but it felt kind of gradual. And then if we go with these general purpose models, they usually require, by the nature of being general purpose, a broader evaluation than specific purpose models, where we might just evaluate on like an NLI test set if we want an NLI model, or a QA, you know, co-ref data set for something that was specific to those tasks. But that raised the question of like, what eval though? Like, what does it mean to be general purpose? What do we want to evaluate general purpose models on? So this is kind of an example of, to illustrate this change, and Anna also talked about this one. This little unicorn is so memorable and so cute. Anyway, so this paper kind of exemplifies this change because it framed evaluation as something like a discovery of model capability. It wasn't like we want to see if the model does the thing we expect it for. It was, what can the model do? Can we figure out some idea of like the constellation of properties that this general purpose model has? Also, many tests were performed, kind of rapid fire, and the result was the model is awesome, right? And it's hard to really know how to interpret that. Also, the evaluation is marked kind of by a set of this type of showmanship, in a sense. Like, wow, let me pull this amazing unicorn out of a hat. You never would have expected there's a unicorn in the hat, right? Which is super exciting. Like, it's very fun. I do appreciate that. But if we like kind of compare this to the way things used to go, like, how would we have tested for something like this Tick's unicorn in the past? We probably would have gone to that community that Anna mentioned, where there's a bunch of people who drew Tick's animals. We would get some number of them, so like ducks and cows and all sorts of things, maybe 100 or so. And then we would split that into a train and test and see if like training on the one side would actually be able to generalize, let's say, to a new animal, a unicorn. So if you train on horses and rhinoceroses or something, can you get to a unicorn? So it wouldn't be so much like just this prompt and just this output, but it would be something like a little bit more controlled, I guess. So this is definitely a shift from going to data sets that were hand curated for a specific thing to what can we find? So with this kind of situation, what are the other results? So the assumption of IAD is increasingly untenable and thus gets ignored. I mean, what does it mean for the unicorn to be IID to a bunch of text for LM? Like, maybe, I don't know. The assumption of held out test is also becoming increasingly untenable, because if we've scraped the entire internet, people just, we like to think of ourselves as creative, but we often just say the same thing over and over and over. So it's very possible that your test example was in the training example. Also, like a lot of the test sets that we care about have been leaked online. So if we say the multi-analyte dev set, it's all over the internet. All those examples are available. The test set is still closed, very closed. It's rare actually to have a fully closed test set. 3 people in the world have access. One of them is me. But like, that is very rare. And even then, it's possible that some example in the test set is just present online. I mean, I haven't checked because that's the idea of a closed test set. You don't look at it, right? But, it is possible. So that's one issue. Also, the access of transfer on these things is getting increasingly implicit or hard to describe. So when we think about the unicorn, what is that transferring to? From text to what? I guess Tick's text or something. Maybe that's something we want the model to do. I don't know, but it's getting kind of tricky. So it makes it harder to distinguish something like rote memorization of the train set, which granted is still super impressive. I'm impressed by these models all the time. I didn't think they would ever get this good. Like, it's still very impressive, but we can't distinguish rote memorization as well from something like generalization to a new axis. So just to put a spicy final sentence on it, it's sort of like transitioning from a scientific mode of evaluation where we had a well-described test that we had various assumptions that we thought were well kind of motivated to something like a car salesman type mode of evaluation. Ooh, open the trunk, what's in there, Awesome. So, I guess putting it another way is the epistemological basis of eval is kind of crumbling, and showmanship is increasingly substituted for arguments. This gives me anxiety. I don't know if it gives you all anxiety, but it definitely gives me anxiety because I like to think of myself as a scientist. NLP has always been kind of both science and engineering, and how we actually weigh those trade-offs and put them together is always something that's been a bit fluid. But yeah, I still want some kind of a real scientific basis on this stuff. All right, so hopefully you're getting a little bit nervous. So I'll transition towards the second part, where hopefully I'll be very nervous. So there have been, this is, I guess, the part that's the benchmark part of GenBench. There have been a lot of fallacies in the way that people are applying evaluation and benchmarking post this new kind of LLM boom. I'm going to talk about a few of them today, but there are probably more. So I will talk about 4. These are them. You don't need to look at them so much. We'll walk through them. But first, I want to talk about like some evaluation preliminaries just to make sure we're all on the same page. Okay, so what do we do when we do eval? So first we come up with a capability we care about. We can call it capability A. At least back in the day, maybe the pre-train fine-tune time or before, capability A was either, or both, I guess, something that was commercially useful. Let's say question answering was relevant for search, which was a commercially viable application, or something cognitively important. So something that external domain experts like psychologists or linguists or something might have thought of as an interesting human capability that we want to see if the model could also learn. So often for those kind of cognitively important things, we had independent evidence from those fields, whatever the domain fields were, that humans have capability A. That's the kind of capabilities we used to be interested in. So then we would try to figure out, how do we test for capability A? So if we want a model to learn it, how do we know if it's learned it? We have to come up with a test. So we would create a test A, and make some arguments that test A was a good test for capability A. So it was a good operationalization of capability A, and that it was construct valid. So that's basically what we meant. So if the kind of logic we would talk about here would be, if humans can pass test A for capability A, that shows something. That shows that the test is in principle passable. So for example, you had on a really interesting example, like how would you say if you've transferred to a new language? One of the choices was never seeing any French. So that would not be a construct valid test, because how are you supposed to learn French without having seen any information on French? Nobody could do it. No model could do it. It's actually just impossible. So having humans pass the test shows some sort of validity at the beginning. Also, IID assumptions that we used to hold, at least if you could argue that they were holding, would indicate, again, that test A is in principle passable. So that would suggest that like the distributions are close enough that you could imagine a model jumping that gap, basically. We also would want to argue, usually quantitatively, because we love quantitative stuff, that the test set was high quality. So you would measure that somehow. I don't know, Fleisch-Kincaid readability or a reasonable, distribution of lengths or something like that. Say it had enough interesting linguistic phenomena that mattered for logical entailment, say textual entailment. And we would try to argue basically any other way that we possibly could that the operationalization of capability A in test A was theoretically sound. So all this stuff is what we would do. I also wanted to point to this paper from Jacobs and Wallach from a few years ago. This is on fairness domain, but super interesting discussion of how we measure, what it means to be construct valid, all this stuff. So if you haven't seen this one, do check it out. So this was kind of step 2. We would come up with a good test. And step 3, of course, test the model on the test. So we want to know if the model has capability A. That would be great. But unfortunately, we can't actually know that from testing. We can only really tell whether our model lacks capability A. So if it does well in the test, that's compatible with model. Like if model passes test A, whatever we decide that to mean, that's compatible with the model having capability A, but it's not proof. So if you're familiar with like some of the kind of history of science stuff, this is kind of akin to Popper's falsificationism. So you can never really prove a scientific hypothesis true. You can just distinguish between some of them and take hypotheses off the table, basically. So yeah, we can say that it's compatible, or it seems like the model might have capability A, but it's not provable. So let's say that model X reaches human level performance on test A. Either it has capability A, or maybe the model cheated somehow, or the test might have been borked, maybe the test creators made some mistakes, or something else happened. This is the portion that used to be called spurious correlation. So when a model did well in a test just because it, the classical NLI example is somehow, if you train on SNLI and there's the word cat in your test example, the model will always say negation. It's just decided that cats are related to negation. But that's like, why? Textual entailment isn't defined such that cats are related to negation, but it was just a statistical property of the training data set that ended up that way. So yikes. So it's possible that we are in number 2, but we think we're in number 1. And so if that happens, we would have made a type 1 error and failed to reject the null, which was actually false. So those are kind of the preliminaries of evaluation. Hope we're on the same page on most of these. And now we can go on to the fallacies. So what are the fallacies that are currently popping up under the current LLM boom paradigm? The first one is that dataset saturation leads to cumulative improvement. So dataset saturation, of course, as a model does max performance on a dataset, a test dataset. So the way this reasoning goes is something like this. Test A was saturated in 2018. All the 2018 models must have had capability A then, because they performed really well. Because all models created after 2018 are so much stronger than 2018 models, they too must have capability A. So nobody actually says this, of course. This would be pretty unfortunate if someone came out and said this, but people do operate under this kind of approach. So they stop testing on old data sets because they assume that they're saturated. So recall, of course, passing tests doesn't prove they have capability, but we also can't assume that model development will be like monotonically increasing and always cumulative and strictly ordered. So it is possible that models will catastrophically forget. It is possible that the next gen model will actually not be as good at, let's say, NLI as the last gen model. These are things that need to be checked. So this paper is a recent example for ChatGPT, how it has seemed to behave or seems to display something like catastrophic forgetting on some test sets. So it seems to be actually getting worse with more training. How could that, what's happening there? We'd have to dig into the details, but it's possible that the fine tuning is overriding things that are actually necessary for those tests. So yeah, catastrophic forgetting is still a thing. We can't necessarily assume just because the data set saturated in 2018 that 2023 models will still do well on it. Okay. I mean, there are times when you might want to retire a data set for a specific capability. Maybe we don't care about the capability anymore. Maybe we have a new one that we can provably, or at least argue, is a kind of superset of that test. So it's a bigger test that includes that sort of test as part. Maybe something was wrong with that test data set. There are reasons we might want to deprecate data sets, but we need to argue for that. You shouldn't just be like, yeah, okay, it was defeated. It's over forever. I mean, it's worth checking again. Okay. Fallacy 2. All evaluation sucks, so anything goes. Ugh, so rough. Test A was shown to have artifacts, enable shortcuts, etc. Therefore, all evaluation is borked, so it's fine to either not test at all or test with crazy tests that haven't been motivated or validated in the least. Eesh, yikes. Again, nobody says this, but people do act this way sometimes. So there are many issues with this, but one of the main issues is this infers from the existence of something, a broken test, the universality that the thing, all tests are broken. This is a hasty generalization. Some tests are obviously broken, but that doesn't mean we should just give up on the process of eval altogether. We still can make better tests. We still can improve things, and we definitely should do so. Okay, fallacy number 3. Ignore the hard tests. Models pass tests A through Y, so they must have nearly human levels of intelligence. They can't pass Z, but who cares? Why bother to test on Z? So yeah, sure, maybe. But you would have to have something. So, of course, recall that models passing tests doesn't necessarily prove they have the capabilities. It's only compatible with that. But we also can't assume anything about test Z, like a priori from tests A through Y. We can only do that if we think that Z is logically related to A through Y. So if we make an argument, say that NLI and QA are super similar, let's say they're underlined by the same human capability, then we might want to say, like, we'd have to make that argument first. I'm not doing that, but one would have to do that. People have done that before. Then you might say, oh, testing on QA is sufficient to give you some information about NLI, maybe an estimated this much. So we don't need to test it anymore on NLI, or we don't need to test anymore on QA. If there's some reason to compare those things or think they're related, then we can ignore certain tests. But otherwise, it's possible that we're kind of cherry picking, right? It's best to explain why we apply and don't apply particular tests. Otherwise, we might accidentally be cherry picking for the easy ones and be like, ta-da, model is amazing. But you didn't test on all these hard things that we know are really difficult that no model has ever passed. So, leaving out tricky tests or important capabilities, we have to watch out for it as we go through. Okay, number 4, more evaluation is always better. Also called the Gish-Gallop, if you know this phrase. So this is maybe a result of my fallacy 3, right? You might have thought, oh, it's really bad to leave out tests. Let's just test on all of them. I've done this one many times personally. This is a fallacy that I always have to watch myself for. But you got to be careful. So this goes, we don't know which test is best. So we'll just grab as many as we can and maybe average the results or something. And that'll tell us all we need to know. Perfect. But this is a rhetorical technique, known as the Gish-Gallop, which is basically when someone attempts to overwhelm the interlocutor with an excessive number of arguments with no consideration for the argument's strength or accuracy. So look, we have like 5,000 tests and they all show this model is awesome, right? But then you look in on one and you're like, oh, but that test's actually really weird. Is that a thing we actually want to test for? Or you look on this other 2 and you're like, oh, those seem to be correlated though. Like, isn't that double counting? And especially if you're just equally averaging, that can have all sorts of weird results. So if capabilities are not disjoint, tests can be super hard to interpret. And not all test data sets are equally clean, valid, or informative. Also, not all tests test equally important capabilities. So, of course, that raises the question, what is important? You might ask, is riddle solving or acrostic poetry generation as important as negation? I would probably say no, based on my interest, but it depends. I mean, if you're trying to make a poetry generator, maybe being able to generate really awesome acrostic poetry is really important. Or if you're trying to make a ticks animal jar, maybe that unicorn eval is the most important eval you could possibly run. So it kind of depends on what you're trying to do, which ones are most important. As an aside, there have been a lot of people really interested in how you kind of aggregate different tests. We had some work on this in the GenBench project a couple of years ago. We were interested in kind of looking at weighted average, sort of like an economics thing where you have different trade-offs of different accuracy points and figure out basically what is the right way to aggregate over time. There's many things one could do here. Some people have also argued that the base kind of simple average is the right thing to do. It is when you don't know anything about the tests, but might be better if we did know something about the tests and then could set up that aggregation appropriately. But yeah, lots of things going on here, but it's not clearly a good thing necessarily to have more eval. It kind of depends on how you do it. Okay. In summary, there are lots of issues right now. Oh, it makes me stressed. With increased pre-training data size, IID and held out test set assumptions are increasingly untenable. Test sets are multiplying and saturating. So I think that the multiplying is somewhat caused by the saturating, but that increases the risk of this like Gish Gallop thing and also increases the use of red teaming eval, which can be super informative, but kind of is more in the way of like usability and user friendliness than like scientific question of whether this thing has a capability. It's more like, does it do a thing that the user likes, right? Or does it do a thing the user hates, something maybe super harmful or racist or something? So these are obviously important, but they're kind of going towards testing the model for different things, different uses. We've also seen this movement from specific capability to transfer learning to general purpose modeling, and all of those things present very serious evaluation challenges, and we don't really have answers for all of these things. There's lots left to do. Also, these fallacious evaluation practices are everywhere. Hopefully, if you see these, you can try to call them out. That's kind of why I talked about them too. But don't worry, all is not completely lost. There are some things we can do. I'm personally looking forward to an exciting new future for evaluation. I'm going to kind of lay out some things that I think are cool that we could do in the future. So there are many problems, but at least these ones I think have some, maybe if not solutions, maybe that was a bit optimistic, at least things we can do to address them. So number one, it's hard to evaluate general purpose models. This is just a fact. It's not because people are, confused or being fallacious or whatever. This is just true. Because what does it mean to be general purpose? I think that the only way we can really get a good answer to that is if we are explicit and define it. So we should devise some sort of well-motivated task taxonomy. So what is it we want the model to do? What are the subtasks of that? So for something like a model of human cognition, we have some versions of task taxonomies for that. Of course, language isn't solved, linguistic isn't over. These things are still evolving and changing, but at least some of those things exist. I think it'd be really great if we came together as a field at NLP, both the people who want to create the biggest possible model that's also commercially viable, and those of us who kind of care more about the science side, and try to devise what the tasks are that we care about. I feel like we used to have some of these things like co-reference resolution, QA, sentiment analysis, summarization, NLI, like we had a set of these things that we liked. But now that we're releasing the models into the world, that might need to change a bit because they're getting used differently. So it might make sense to have some coming together on this. Second, data sets are saturating. Nobody questions that the models are getting better in some sense, just people argue about what that means. But data sets are saturating means we need more data sets. We should still test the ones that we think are saturated, of course, at least sometimes. We shouldn't just drop them without being sure, but we do need more tests. And so there's lots of room to make more tests for things. This is very cool. Fallacies abound, yeah, just try your best to point them out. I still check myself on those all the time. People often, another problem, training data sets too big. Oh gosh, how do we check? Keep investigating anyway, just to say the same thing that Anna said. You can test these things. Maybe the big fancy actors in the space that are pre-training models are hiding what they're training on, but we you might kind of know if you think about it for a second what it could possibly be, right? Like what kind of data is actually clean enough? You can test things that are openly available. There's some cool data exploration tools at the Pile, for example. I think Duca, who's here somewhere, has been doing some work on that too. Like there are things we can do even if we don't know. We maybe kind of know. Okay. So also too many evaluations, what does it all mean? For this one, I think there's a very specific solution, which is also maybe kind of a research program. Hopefully some of you will be excited in this one. This is something that I've been really excited about and working on recently, and that's do meta evaluation. This is super cool. Okay. So just to give an example of one of the solutions here for the data sets are saturating problem. So that's normal. The data sets, test data sets have a life cycle. It looks something like this. First, you define the capability, then you develop the test, then you test it on models. We already talked about those 3 steps, 1 through 3. But after you've done that over time, maybe the test starts to saturate, maybe issues with that test are found. So you have to determine what is wrong and what it tells you about that capability or what it tells you about the models, and then you create a new test and redefine it again. So the way that this can generally go, where it sort of works, maybe, is things like from the transition to multi-NLI from SNLI. Our argument, at least when we created a new data set, was this is the same capability. It's set up exactly the same. We just have discovered some problems with the current one, and we want to make a new one. We want to extend it in certain ways. We're explicit about what the extension was, but the 2 data sets were supposed to be targeting exactly the same capability. They were both 3-label natural language inference from crowdsourced data. So, when you want to deprecate something, you have to make an argument that you're actually replacing the old thing. So of course, despite our best efforts, no test is ever perfect. Also, test creators, at least I guess maybe speaking for myself, we aim to make a test that falls into a Goldilocks zone of difficulty. It's not so hard that no model can possibly pass it, but it's not so easy that it gets beaten completely immediately. So it is kind of assumed that eventually models will make enough progress that you might need to make a new data set. Also, of course, our understanding of underlying capabilities will grow and change from talking with domain experts or something else. We can also learn how to better operationalize tests. And, sometimes tests should actually be tailored to particular models. Like maybe something about the architecture, it requires a certain kind of test. So let's say you train on super, super long sequences and all your test sequences are like 4 tokens. Let's say your model does really badly. Why? Maybe the distribution is just off. So you might sometimes want to kind of thread this needle where the test is both general for all models, but also specific to models. Kind of depends. Another thing that you can do about data sets is check out this GitHub link that Duca, Tom, Xenia, and I have been working on. It's a repo to track data set issues. So sometimes this helps you figure out whether a data set is saturating, whether it has problems, this sort of thing. So sometimes when you're digging through the errors your model makes, you realize that some weren't your model's fault, but they came from data set issues. You can upload them here so everyone else in the community can check and find out. We don't have to keep replicating these same discoveries like, oh, this broken data point over and over and over. So please do share your errors if you find them. Last problem. Oh my gosh, so many evaluations. What do we do? So meta-evaluation is the process of evaluating your evaluations. This means doing ongoing validity checks for the life of the data set and possibly hot fixes, versioning things. People do this. Comparison across test sets for the same capability. So figure out if you have like 5 test sets for QA, do they rank all models the same? This kind of like meta-analysis stuff. Also, it's important to check in with domain experts on the state of the art in their field. So has anything changed since these test sets were created? And also just general synthesizing of what we have learned from providing a lot of tests. So I've got a bunch of examples on these. Some of them are here today or tomorrow or whatever during the conference. This one was a meta-eval project, which was looking at syntactic acceptability judgments. So BLIMP and Syntax Gym are huge, important test suites for these capabilities, but their examples are often presented in isolation, but our current models present sentences in context. So with like maybe lots of sentence, lots of text in the window. So if we adjust the context by prefixing different kinds of text, does that affect the results that we get on these test suites? And the answer is yes. Do check out the paper to find out. But like, if the test doesn't fit the way that the models are currently run, you can do things to retrofit and understand what's going on there. This one, also very cool, is looking at the robustness of named entity replacements and in-context learning. So everybody's excited about in-context learning these days, with performance looking very promising. But of course, the choice of demonstrations and their relationship to the query is very kind of unknown. Which demonstrations you pick can impact the accuracy that you have. We did a bunch of named entity replacements for things like in the baby tasks, which be like Jason has 20 lollipops, and now he gave some to Denny, now he has 12. How many did he give to Denny? If you replace Jason with like Bob, it might completely change the results. So, that's something to keep aware of. Not a lot of robustness sometimes. This is one that I'll be presenting in a few days on fairness and toxicity. So there are many, many fairness and toxicity data sets. They don't actually target the same capability often, so you do need to test on many of them. But any particular group that's proposed a large model hasn't probably tested on all of them. So we went back and kind of did a check. if we do a large scale test on all of the things, where are the gaps? Found a bunch of gaps, made some more test sets to fill those gaps, tested everything again. And now that we have an idea of like, make sure that more demographics are covered than had been covered previously, that like combinations of demographics are covered, this sort of thing, we can actually work on testing mitigations and finding out which mitigation is right for which model. But this is a lot of work. I have to go back to the models a year later and check everything and do all this meta-analysis, basically. So yeah, if you're interested in this one, definitely find me after or come by. And last one, Kaiser-san, who might be here, presented this one in the poster session, but they're also going to present at Connell later. This one was looking at different compositionality benchmarks and trying to figure out how much they can tell you about each other. So do models, like do the benchmarks rank models the same, or do they rank models differently? And does that mean that the compositionality that those data sets operationalizes is the same kind of notion of that capability or different ones? So this is building on work actually by Robin as well on concurrence. So definitely check this one out. This is also really cool. Okay, sorry, I feel like I'm slightly over time. So takeaways. Evaluation is hard, but don't give up. It's still a thing we can make progress on. It kind of means that we have to take stock of where we are, what we want our models to do, but we can do that. It's not impossible. There are some things that are still tricky, but we can make progress. Okay, watch out for those fallacies. I commit some of them all the time. Probably you all do too. Try to catch each other when we're doing it. Keep investigating that training data. It does matter. If we want to know about generalization, we can't tell if something's generalized unless we know what the training data was. There are many best practices for data set creation. Do use them. They're important. And finally, meta-evaluation can help. When we have existing evaluations, we should figure out how they play together, how they don't play together. And then that can also help us figure out what to test for that we don't already have data sets to test for. So yes, that's it for me. Thanks so much for listening.
Thanks, Adina. We have time for a couple of questions, and I'm also checking online. If you have any questions online, please add them. Otherwise, let's see ahead.
So thank you for the incredible and fascinating talk. This is very focused on sort of benchmarks and evaluation sets where we throw our models at them every time. It's completely automated. I'm curious to get your thoughts of how many fallacies also apply to things like user studies, where we build a system, we get some real physical human beings in the lab, get them interact with it. Does that avoid some of these? Like obviously you've got new data, so it's not has that risk, but do others apply? And what are your thoughts? Thank you.
Yeah, so if we're thinking about user studies or maybe like psych studies even, I guess I could. I can't think of an example right off the bat. Definitely this last one can. It's always a possibility. I imagine it could, yeah, but I can't think of good examples. Did you have something in mind, or? Oh, sorry to make you run.
No, I didn't have anything in mind, but it was more that our community for a long time is focused on automated metrics. And of course, you look at like Kai and the HCI community and everything's user studies. And maybe this is an argument that we should move more in that direction as well.
Yeah, so I think that there is, now that you mentioned that, I do think from the red teaming perspective, there is something kind of similar, which is to the first one, the cumulative improvement one, we do kind of assume that people's agreement is somehow important, or that we can test on a small number of people, like one sometimes, and that will be the right answer. A lot of red teaming stuff is done with literally one person. So that thing is sort of similar to this cumulative improvement, and that we imagine this small sample will be fully representative of everyone, I guess. But of course, there's all sorts of efficiency stuff in there too. I would love for there to be a closer connection between NLP and Kai stuff. I think that they have learned a lot of things that lots of people are reinventing when they're trying to come up with red teaming, and it is not very efficient. Yeah.
Thanks. Yes, well, before I go to the next question, I should say if the presenters for the spotlight presentations can come closer to the podium, I appreciate it. In the meantime, yeah, we have time for maybe one or two quick questions.
Just asking the obvious. You said keep investigating the training data, but it is practically impossible in the age of GPTs. Do you have any best practices that we can follow?
I mean, you can't necessarily investigate all of it, but at least for the stuff that we know is language data, or the stuff that we know is image data. I mean, languages may be easier. We do know that they're just scraping everything that they possibly can. So everything that's open source, they're definitely using that. They're probably using other stuff as well, especially for preference tuning. And that is really hard to get your hands on. That stuff is super secret. And I mean, none of us know what's in there basically, but at least the pre-training data can be checked still.
It is all seen, right? Because all training data is generally over the web. So basically we are saying they have seen all of the training data. That's the sort of eventual conclusion.
I guess so. Yeah. Which then leads us to the question of like, yeah, is eval just completely broken? What does it mean to generalize? I hope not, but there is a scary possible future in there. Yeah.
Sorry, I'm afraid I will have to cut it short here to get back in our schedule, but please reach out to Adina later. And in the meantime, join me in thanking Adina. Thanks.
Yeah, happy to chat more. Thank you.